Hi there, and welcome to this new session in which we are going to delve deep into generative adversarial neural networks. In the previous session, we had seen how we made use of the variational autoencoders to generate these kinds of outputs, which are in fact MNIST digits, from just an input noise. So what we had was this kind of encoder decoder structure where we had some input images here, like this one for example, some inputs, and then we trained the model such that the outputs look like these inputs. And then once training is done, we could take off this encoder and then just pass in a noise signal in here and then generate new outputs like what we have here, which look like those from the original data set. And in this section, we'll be seeing how to build a new set of or a new category of generative models known as the GANs. And we'll use them to generate images like this one which we have here. You should note that all these images are images of people who do not actually exist. But before we dive into practice and see how to build models which can build this kind of realistic looking images, we should start by understanding how this generative adversarial neural networks, that's GANs, work. Now, these GANs were first introduced in this paper by Goodfellow et al., where the GAN architecture was first proposed. And to understand how the GANs work, let's make use of this figure from Louis Bouchard's post. Now, let's suppose we have the bank which produces real money. You see here we have this real $100 bill. And then on this other end, we have the thief who produces fake money. You see here, this $100 bill has this man with a mustache, which isn't the case of the real dollar bill. And because differences like this, and say for example this compared to this, are very clear or can be easily seen, this police officer is able to detect that this money is fake. But when this police officer detects that the banknote is fake, he or she says that it's fake because we have a mustache, for example, because we have this word fake written on it, because this 100 has a fake around it and stuff like that. So it tells the forger or the thief what needs to be ameliorated in order to make sure that the next time this thief presents this fake money to the police officer, the officer thinks it is maybe this real money. And so if we suppose that real money takes a value of 1 and fake money takes a value of 0, let's change the color, fake money takes a value of 0, then let's say in the first years of production of this fake dollar bills, the police officer correctly says, okay, this is a 0 and this is a 1. That's it's very evident at the beginning. But then with time, this thief gains experience and now produces fake money which looks just like the real money. And this now pushes the police officer not to be able to distinguish between the real and the fake any longer. Now, although we do not advocate for these kinds of malpractices, it turns out that this is the way the GANs actually work. And in our case, we'll replace this generator, or we'll replace this thief by a generator model, which is a neural network. So this is going to be a neural network, and we replace this police officer by a discriminator, which also is a neural network, specifically a binary classifier, which takes in some input and says whether it is real or not. Whereas our generator here takes in some random inputs and then learns to output this banknotes such that the discriminator thinks that it is real. Now we shall head on to the GAN lab, which is a project by Min Soo Kang et al. And we'll consider some very simple example. So here we'll suppose our data distribution is this here. See that? And then notice how we have a generator, we have a discriminator, and then the generator takes in some random noise and then outputs this sample, and then the discriminator takes in the sample and says whether it is real or it's fake. Now, apart from this fake samples, it also takes in the real samples and then also says whether it's real or it's fake. Now the weights of the generator and the discriminator are being updated such that after some time, these samples which are going to be produced will look very much like this right here. So let's go ahead and click on run and we see what we get. You see how we start with the training. Let's take all this off. See, we start with the training. For now, the fix, let's pause and start over. Let's restart that. Okay, you see initially we get in this kinds of outputs. You see this output, you could look at this here. So this is a kind of sample generated, and this is that of our real data right here. And one thing we notice is that at times, as time goes on, you have here both the green and the purples which are considered to be real, and then here's only the purples considered to be fake. So this discriminator now starts making errors when it comes to saying whether a given sample is real or not. Whereas on the other hand, the generator is now producing samples which look much like the real samples. And it's because of this competition between the generator and the discriminator that they actually called the GANs, generative adversarial. This adversary comes from this competition between the generator and the discriminator, and it now leads to the generator producing samples which look very much like the real samples. One other point you should notice that as we carrying out this training, overall we have two main parts. We have this block right here. Let's take this block. We have this block which consists of wherein when the discriminator takes in this real and then outputs some value, the output from this is used to update the parameters of the discriminator. And then when the discriminator takes in this fake samples, this output here is used now to update the generator. So we have this block wherein we update our discriminator, and we have this other block wherein we update our generator. So with that, now we could pause this and you could change the data distribution. And so again, in comparison to with the VAEs where we had this encoder and then the decoder, well, if we have a distribution like this one, so we have some input, we want to have, or we want to be able to output or get outputs which will look similar to this input distribution. And then after training this encoder decoder, we now break this up and then make use of only this decoder to now generate output which are similar, or whose distribution is similar to that of this real inputs right here. Again, another important point to note is the fact that after training, after a certain number of epochs, at some point when the reals and the fakes look very similar, the discriminator now becomes somehow confused. As if you notice here, you find some green patches. You see, you have some green patches purple patches. Here we have some green patches and purple patches. So it's no longer able to distinguish between the reals and the fakes. And so instead of as before, or as at the beginning, where it was able to say this is a 1 and this was a 0, now it sees this as a 0.5 and this as a 0.5. It becomes confused. And so in fact, the aim of our GAN training process will be to ensure that the generator wins the fight. It should be noted that most very cool applications of GANs are in the domain of image generation. And so we'll look at some of these applications in this article by Jonathan Hoy. GANs can be used in creating anime characters. You see here, we have this anime characters which have been generated automatically using GANs. And so this means that similar to what we had here, we're going to have a real data set which produces images similar to what we have right here. Let's get back here. Similar to what we have right here. And then we're going to have a generator which will learn over time to generate images which will look like the real images. And that's how we get to have images like this one. Now from here we also have pose-guided person image generation. Here for example, you'll notice that we have this input image, and then if we want to have this same person but with a different pose, then we could pass in this pose and then get this output right here. So you see that we have this input, that's this image with this different pose, and then this is being generated. Another application is in cross-domain translations. So you see here we have this input where we have this two or say 3 zebras, and then we are able to transform this input image automatically into this other domain where we instead have horses. And so this image or this input or this output rather has been generated from this input. And this could be done in the reverse direction, as we would see here. We see you could get from zebra to horse as we had here, and then from horse to zebra. Then we have another example. This is a star GAN which permits us to carry out translations or transformations where we modify specific high-level features of an image. So right here you see we have this input, and then we add, for example, blonde hair. So it changes the gender, modified such that this male becomes a female. Aged, so he is aged. And talking about aged, you could build an application which tells you or which shows you what you would look like after say 20, 50 years. Then here we have pale skin. Another or some other modifications we could have here is angry, happy, fearful, and that. So that's it. You see, making use of this star GAN, you could carry out this kinds of transformations on an input image. The next we have this pixel DT GAN, which creates clothing images and styles from an input image. So you see we have the source image and we have this different images which have been generated from this source. We have other examples right here, as you could see. And then we have super resolution. Now for super resolution, GANs are being used to increase the resolution of an input image while making this higher resolution images more realistic. So you see this image, for example, this bicubic, this one right here, which has been gotten using the bicubic method, and then we have this other image which is using ResNet. And then now you'll notice that there is some difference with the kind of output we get using a GAN. Notice how this image here looks more realistic or looks much more like the original as compared to what this other two non-GAN methods produce. To even get a much clearer difference, notice this part here where we have this water pouring. You'll notice how this looks much more realistic as compared to using a classical neural network like the ResNet. Then from here we move on to the next application, which is that of generating faces, but this time around very high definition faces. So here you see you have 1024 by 1024 images generated. You see this images of people who do not actually exist, which have been gotten using a pro GAN. That's a progressive GAN. Now we move to the next. We have style GAN, which even comes with much better resolution and with some styling. So from here we go on to high resolution image synthesis, where we could get receive this semantic map, and then from here we generate this output we have right here. Then the next GANs, which as we've seen already takes this kinds of semantic maps and then produces this output. You see, this is the ground truth. This is the exact output, and this is what the GAN produces. See that? See, from here we're able to produce this, from this we're able to produce this. Now this kind of technology could be applied in video compression, in a sense that during a video call where we have this input, so we're supposing that we have this is a sender and then this is a receiver. We separated by this dotted lines right here. So we have this input right here, and then we carry out key point extraction where we get this key points, as you could see here, and then this is what's been transmitted via the network. So instead of transmitting this input, we transmit this key points, and then making use of some keyframe which has been passed initially, we combine this key points with the keyframe to produce now this output right here, which looks like this original input which we wanted to pass. And so now at the receiving end, we are able to get this here at a much lower bandwidth, since we are taking in only the key points and not this whole input image. Then we also have applications in text to image, where we could pass in a text like this flower has long thin yellow petals and a lot of yellow anthers in the center, and this generates this kind of output. Now talking about this kinds of applications, we could check out Crayon.com, which is in fact a DALL-E mini model, where we'll be able to create much more realistic outputs. So let's click on this, and while this is loading, we could check out on the other applications. The next application, text to image, we've seen this already. Face synthesis, you see right here we get with a single input image, we create faces in different viewing angles. So for example, we can use this to transform images that will be easier for face recognition. So if we suppose that we get in this kind of input, let's say we get this kind of input, we could generate, or we could convert this, for example, into this one here, such that it will be easier for a face recognition model to do its job. Now from here we go to the next one, image inpainting. Okay, so right here we have this inputs. Let's increase this, take this off. So as we're saying, we have, let's pick this one for example. We have this input right here, but we have this patch which has been taken off, and now making use of a GAN, we are able to generate an output which will be like this input without the patch. So it's just like the GAN takes this patch off, and as you could see, the GAN does its job quite well. Let's reduce this. There we go. Before we move on, let's get back to this output created at Crayon.com, and you can see that this DALL-E mini model produces even much more realistic images. Then we move on to the Discord GANs, where we could create outputs which match the style of a given input. So supposing you want to go out on a little trip, you want to say take this bag, and you wanting to get some ideas of the kind of shoe you could put on, then you could make a call on the Discord GAN and you would get this kind of output based on your input. So this is uh, a model which is similar to the cycle GAN, which we had already seen right here, and where we were able to leave from one domain to another. One other fun project will be to generate emojis from input images. See here, we have this input image, for example, and we have this emoji which is generated from the input. Then another very interesting application will be in deblurring. So right here, we suppose that we have this input image which is clearly blurred, and then we want to deblur this image. You see that we're able to produce this kind of images making use of GANs, and you can see from those images here that the GANs do this job quite well. Another application is in photo editing, and so now you do not need to be some expert in photo editing to carry out some of this photo edits. All you need now is some GAN and you're good to go. Apart from image generation, GANs too can be used in music generation, though in this course we shall focus on image generation. Then the medical domain, GANs could be used in anomaly detection. And that's it for this section. In the next section, we are going to look at how these GANs are actually trained in practice and the type of loss functions we use when training this GAN.